Welcome everyone to Sustainability and Engineering. And thank you for joining this session. Today, I want to talk about something that almost every HVAC engineer has faced at some point in their career, but very few of us actually talk about openly. We have all seen projects where the HVAC system is fully approved, properly installed, and even commissioned, yet the building still struggles with comfort issues, high energy consumptions, frequent complaints, or long-term reliability problems. And let me be very clear, this discussion is not about poor workmanship or site execution. What we are really talking about today is unit selection. Those early decisions we make during design and submittals, the assumptions we accept, the shortcuts we sometimes don't even realize we are taking. Because these decisions don't affect approval drawings, they quietly define how building will perform for the next 15 to 20 years. In this session, we'll break down why approved systems still fail, what is often missed during selection, and how engineers can move beyond catalog choices to make truly performance-driven HVAC decisions. So let's dive right in. In almost every project, there comes a moment, usually after handover, when the complaint starts coming in. The space feels cold, but somehow it's still humid. The HVAC unit seems to be running all the time. Energy bills go up, occupants are uncomfortable, and very quickly, the HVAC system becomes the main point of concern. What's interesting is that when we go back and review the documents, everything looks correct. The units are approved, the calculations are submitted, the drawings are signed off. On paper, nothing is wrong. And this gap between what looks right in the documents and what actually happens on site is where the real engineering begins. Because at that point, we are no longer dealing with approvals or paperwork. We are dealing with performance. And performance always exposes what was missed earlier. Authority approvals play an important role in our projects. It confirms that the design meets minimum code, standards, and regulations. But approval alone does not tell us how the system will actually behave once the building is occupied. It does not verify how the unit will respond to real heat gains, real humidity levels, part load operation, or the way occupants actually use the space. True performance depends on something much deeper. It depends on how accurately we interpret the cooling and ventilation loads. How well we match unit characteristics like airflow, coil performance, and modulation to those loads. And how realistically we anticipate the building's operating patterns, schedules, and usage. This is where engineering judgment comes in, because compliance gets a system approved, but engineering decisions are what make it perform. Most HVAC failures don't actually begin on site. They usually start much earlier, quietly, during the unit selection stage. They start when we rely too heavily on catalog data without fully questioning the assumptions behind it. When safety margins are added without really understanding what they are compensating for, and when numbers are accepted but behavior is not analyzed. At that stage, nothing looks wrong. The unit appears adequate. The selection sheet looks complete and the submittal gets approved. But once the unit is installed and the system is operational, those early assumptions begin to show their impact. And by then, the room to correct the problem becomes very limited. Changes are costly, retrofits are difficult, and what was once a small selection decision turns into a long-term performance issue. This is why understanding where failures truly originate is so critical for engineers. One of the most important things to understand in HVAC design is that cooling load is not a single number. Cooling load is made up of different components and each one behaves differently. Sensible heat affects air temperature, latent heat affects humidity and moisture levels, ventilation loads introduces both heat and moisture into the space, especially in hot and humid climates. Different HVAC systems and even different unit configurations handle these components in very different ways. Some systems are better at temperature control, others are more effective at moisture removal. And ventilation loads often require dedicated strategies. When this breakdown is ignored and selection is based only on total tonnage, the result is predictable. The system may meet the calculated load on paper, but it struggles to control humidity, comfort, or energy consumption in reality. This is one of the most common reasons why HVAC systems that are fully approved still fail to perform as expected. Sensible heat ratio, or SHR, tells us how a cooling system divides its capacity between temperature reduction and moisture removal. In simple terms, it explains how much of the unit's cooling effort is used to cool the air and how much is used to remove humidity. Every space has its own requirement. Some spaces are dominated by sensible heat, others carry a high latent load due to occupancy, fresh air, or local climate. If the selected unit SHR does not match what the space actually needs, problems are inevitable. The room may reach the set temperature, but it will still feel uncomfortable, sticky, or heavy. And no matter how much tonnage we add, the discomfort will not go away, because the issue is not capacity, it's how the capacity is being used. This is why SHR alignment is critical, and why many systems fail even though the total load calculation appears correct. When we look at HVAC catalog data, most performance ratings are given at what is known as T1 conditions. T1 represents moderate outdoor temperatures and controlled indoor conditions. These ratings are useful for comparison, but they do not represent how systems actually operate in hot climates. In regions like Middle East, HVAC equipment is exposed to much harsh conditions. This is where T3 conditions become critical. T3 performance accounts for much higher outdoor ambient temperatures, higher condenser entering air temperatures, increased compressor and fan loading. Under T3 conditions, the same unit delivers less cooling capacity and consumes more power than it does at T1. So when a unit is selected based only on T1 data, it may appear perfectly adequate on paper. But once installed at site, its real capacity drops exactly when the cooling demand is at its highest. This is why selecting equipment based on T3 performance, not just T1 ratings, is so important. T3 selection ensures that the unit can actually meet the design load during peak summer conditions, set points can be maintained without continuous operation, energy consumption remains predictable, and long-term reliability is not compromised due to constant overload. In simple terms, T1 tells us how the unit performs in ideal conditions, but T3 tells us how it performs in real world. And in hot climate projects, it is T3 performance that determines whether a system succeeds or struggles. One reality that is often overlooked in HVAC design is that systems almost never operate at full load. For most of their life, HVAC systems run at part load conditions, often 80 to 90% of the time. Now, let me give you a simple site example. Imagine an office space that has a calculated load of 8 ton. Instead of selecting an 8-ton unit, a 12-ton unit is selected to be safe. On paper, this looks conservative. On site, the behavior is very different. The oversized unit cools the space very quickly and reaches the set point in short time. The compressor switches off before sufficient moisture is removed. Humidity builds up even though the temperature looks fine, because the load is really close to 12 ton. The unit keeps starting and stopping. This short cycling increases energy consumption, creates comfort complaints, and puts unnecessary stress on compressor and electrical components. Now compare that with a correctly sized 8TR unit. The unit runs longer and more stable cycles. It removes both heat and moisture effectively, temperature and humidity remain consistent, and the system operates closer to its designed efficiency range. This is why proper sizing improves comfort, reduces energy use, and extends equipment life. In HVAC design, oversizing does not create safety, it creates performance problems. Fan static pressure is one of the most commonly underestimated parameters during HVAC unit selection. In many cases, units are selected using a nominal or typical static pressure value, assuming ideal duct routing, short runs, and clean components. But real systems are never ideal. In practice, fan static pressure must overcome the combined resistance of the ductwork, the cooling or heating coils, filters, especially as the load with dust over time increases, as well as the sound attenuators, dampers, VAV boxes, and other terminal devices. Each of these elements adds pressure loss to the system. When these losses are underestimated during selection, the fan simply does not have enough capability to deliver the required airflow. On paper, everything looks fine. The unit is approved, the fan is operating, but at site, the space never receives the designed air quantity. This leads to rooms that feel under-conditioned, poor air distribution, and systems that appear to be working but never actually perform. This is why realistic static pressure calculations and allowing for dirty filter conditions are critical to reliable HVAC performance. Coil selection is often misunderstood as simply choosing the number of rows. In reality, it is one of the most critical and most sensitive part of HVAC unit selection. A coil's real performance depends on several interacting factors. The phase velocity of air across a coil, fin spacing and fin density, the number of coil rows, the refrigerant or chill water temperature difference, and the allowable pressure drop through the coil. If phase velocity is too high, air passes over the coil too quickly. This increases the pressure drop and can lead to moisture carryover, where condensate is pulled back into the airstream instead of draining properly. On the other hand, simply increasing the number of rows is not always the solution. More rows increase airside resistance, raise fan power requirements, and can significantly increase noise levels. When coils are poorly selected, the system may look adequate on paper. The nominal capacity may appear sufficient, but in real operation, the increased pressure drop and airflow limitations reduce the usable cooling capacity. This is why careful coil selection is essential, not just for meeting capacities, but for achieving stable airflow, proper humidification, dehumidification, acceptable noise levels, and overall system efficiency. DX systems are among the most sensitive HVAC systems when it comes to selection accuracy. Because cooling is achieved directly through refrigerant expansion, even small selection errors quickly show up in real operation. When a DX unit is oversized, it cools the space too quickly and shuts off before it has time to remove sufficient moisture. This short cycling reduces dehumidification, increases power consumption due to frequent starts, and places repeated mechanical and electrical stress on the compressor. Over time, this leads to higher energy bills, unstable comfort, and premature equipment failure. On the other hand, undersized DX units struggle in a different way. They operate continuously, often at or near full load. While this may improve the moisture removal initially, it results in poor temperature control during peak conditions, continuous high energy consumptions, and accelerated wear on compressor and fans. This is why DX system requires particularly careful selection. Accurate load analysis is essential. The unit's sensible heat ratio must align with the space requirements, and fan static pressure assumptions must reflect real duct and filter conditions. When any of these are overlooked, DX system may still be approved and installed, but they will rarely deliver stable, efficient long-term performance. VRF systems are often perceived as flexible and forgiving, especially because of their ability to modulate capacity and serve multiple zones. This perception sometimes leads to assumption that VRF system can adjust themselves even if selection or layout is not perfect. In reality, the opposite is true. VRF systems require very careful system-level engineering. Performance is not determined by single unit, but by how the entire system is configured. Outdoor unit capacity must be correctly matched to the connected indoor units. Indoor unit combination and diversity ratios must remain within allowable limits. Piping lengths and equivalent lengths directly affect refrigerant flow and capacity. Vertical height differences introduce additional pressure and oil return challenges. Each of these factors influence how efficiently refrigerant is distributed all across the system. Each of these factors influences how a system works. A VRF system can be fully approved, installed, and commissioned, yet still underperform simply because the overall system balance was not engineered correctly. When that happens, capacity is unevenly distributed, some zones struggle, others overcool, and the system never operates at its intended efficiency. This is why VRF systems should never be treated as plug-and-play solutions. Their success depends far more on system design and coordination than on individual indoor and outdoor units themselves. One of the most common misunderstandings in VRF design relates to diversity. The system efficiency of a VRF relies heavily on assumption that different zones will peak at different times. Some spaces cool down earlier, others later, and the system continuously modulates to match that varying demand. When this diversity actually exists, VRF system performs very well. However, problems begin when all indoor units peak at the same time. In that situation, the outdoor unit is forced to operate near full load for the extended periods. Capacity modulation becomes limited, energy consumption increases, and the system loses much of the efficiency advantage it was selected for. When this happens, the VRF system effectively behaves like an oversized DX system, but with significantly higher initial cost and complexities. This is why diversity should never be assumed. It must be evaluated realistically based on the space usage, schedules, and occupancy pattern. Without true diversity, the benefits of VRF system quickly disappear. Chill water systems often give a sense of comfort and safety because of the central plant configuration. There is redundancy at the chiller level, there is flexibility in distribution, and it's easy to assume that the plant will compensate for any issues downstream. However, in practice, terminal unit selection still plays a critical role in overall system performance. If the chiller water temperature difference is not aligned with the design intent, or if the coils are oversized, or if the control valves are poorly matched, heat transfer at the terminal level becomes inefficient and unstable. This leads to poor temperature control and inconsistent comfort across spaces. The central plant continues to operate, but it cannot correct the terminal level problems. In other words, the plant can supply chill water, but it cannot fix poor heat exchange, bad valve authority, or incorrect coil selection. This is why even in chill water systems, good terminal unit selection is just as important as plant design. Fan coil units are often selected based on just two parameters, airflow and cooling capacity. On paper, that may seem sufficient, but in real operation, FCUs usually fail for very different reasons. Many issue arises due to excessive noise levels, poor control valve authority, incorrect chill water flow rates, or sound power data that looks acceptable in catalogs but does not reflect real installation conditions. When valves are poorly sized, control becomes unstable. The FCU hunts, temperature fluctuates, and occupants feel discomfort even though the system is running. And very often, the first complaint is not temperature, it's noise. A rattling, whistling, or constant fan sound is usually noticed long before anyone talks about cooling performance. By the time thermal discomfort is reported, the dissatisfaction has already set in. This is why FCU selection must consider acoustics, control stability, and realistic operating conditions, not just airflow and nominal capacities. Getting these details right make the difference between quiet, comfortable space and a system that generates complaints from day one. The difference between an AHU and a FAHU is far more than just a naming convention. An AHU typically handles mixed air, a combination of return air from the space and a portion of outdoor air for ventilation. Because a larger part of the air has already been conditioned, the thermal and moisture loads are relatively moderate. A FAHU, on the other hand, handles 100% outdoor air. This single difference changes everything. Outdoor air carries significant higher latent load, especially in hot and humid climates. As a result, FAHUs require very different design considerations. Coils must be sized not only for the temperature reduction but for effective moisture removal. Filtration stages usually need to be more robust, increasing pressure drop. Fan power requirements rises due to higher airflow resistance. And energy recovery systems often become essential to control energy consumption. When FAHU is treated like a regular AHU using similar assumptions for coil sizing, pressure drop, or fan selection, the system almost always struggles. This is a very common and very costly mistake. Understanding this distinction is crucial because FAHUs are often at the heart of the indoor air quality, comfort, and energy performance across the entire building. One important reality in HVAC design is that filters are truly clean only on the day they are installed. From that moment onward, dust and contaminants begin to accumulate. As this happens, the pressure drop across the filters steadily increases, and the amount of air the system can deliver gradually decreases. If the fan has not been selected to accommodate dirty filter conditions, this reduction in airflow becomes unavoidable. What makes this issue particularly difficult to identify is how it develops. The system does not fail suddenly. There are no immediate alarms. Performance simply declines over time. Space slowly begins to feel unconditioned, cooling capacity appears to drop, and the problem is often blamed on the equipment aging or poor maintenance. In reality, the root cause is usually much earlier. A selection decision that did not allow sufficient fan capability for filter loading. This is why designing for clean and dirty condition is essential. It ensures stable airflow, consistent comfort, and reliable performance throughout the system's life, not just at commissioning. Controls are not optional accessories that are added after the HVAC units have been selected. They are a core part of how the system performs. Even the best selected units can behave poorly if the control logic is weak or mismatched to the system design. Poor control strategies often lead to problems such as simultaneous heating and cooling, unstable or drifting space temperatures, excessive energy consumption, and frequent alarms or manual overrides through BMS. When this happens, operators lose confidence in the system, and the building quickly moves away from its intended operating strategy. This is why unit selection must always align with the control philosophy. Capacity modulation, airflow control, valve behavior, sensor placement, and sequencing logic all need to be considered together, not in isolation. BMS integration should not be treated as a separate stage. It must be part of the selection and design decision from the very beginning. When equipment capabilities and control strategies are aligned early, system operates smoothly, efficiently, and predictably over the entire life cycle of the system. Most HVAC failures are not the result of poor quality equipment. In many cases, the equipment itself is perfectly capable. The real issue usually lies in how the equipment was selected. Too often, selection becomes a catalog-driven exercise, where the focus is on matching numbers, capacities, airflows, efficiency ratings, without fully understanding how the system will actually behave in real operating conditions. Software can calculate loads, catalogs can present a range of options, but neither can replace engineering judgment. True performance comes from understanding how loads vary, how systems operate at part loads, how components interact, and how real buildings are used over time. When selections are made with this mindset, system performs reliably. When they are not, even approved and well-installed systems can struggle. This is fundamental root cause behind many HVAC performance issues we see at site. One of the most important lessons in HVAC engineering is this: approval does not automatically mean a system has been properly designed, and even a well-designed system does not automatically guarantee good performance. HVAC unit selection is not simply about choosing a product from catalog. It is about understanding and predicting how the product will actually behave across different climates, under varying load conditions, and throughout real day-to-day operation. When selection decisions are made with this level of understanding, system becomes stable, efficient, and reliable. And when the selection logic is right, most of the problems we typically face later, like comfort complaints, high energy use, repeated adjustments, and site dispute, largely they disappear. This is the difference between selecting equipment and engineering performance. If this session has helped you look at HVAC unit selection in a different way, I encourage you to like, share, and subscribe to the channel. These are the details that truly separate average HVAC system from systems that perform reliably, efficiently, and consistently over time. As engineers, our responsibility goes beyond getting drawings approved. It's about taking ownership of how our systems behave in the real world. If we shift our mindset away from approvals alone and towards true engineering accountability, the quality of projects and our profession improves. Let's design with intent. Let's select with understanding. Build it right, build it once.